Okay, well, I'm very happy to introduce the last speaker of this morning's session. It's Olivier Hénot. He's going to tell us about rigorous computation of unstable manifolds for equilibria of delay differential equations. So take it away, Olivier.
Thank you. Yeah, so actually, a lot of things I'm going to talk about has been kind of previously mentioned in the context of ODEs, so that's cool. It will be easier to present. And also, this is a work that has been done with Jay and Jean-Philippe. Okay. So first of all, let's see what we're dealing with. So we're going to look at the simplest delay differential equation possible. So we have one constant delay, and it's a scalar differential equation. F is assumed to be a polynomial, and if not, it's okay if you have an analytic function that is only comprised of elementary functions. So if you have some exponential terms, things like this, you can still turn it into a polynomial. So the class of function that we're dealing with here is actually larger than just polynomials. And U sub t is just a convenient notation to represent the history function. And everything I'm going to mention, of course, applies if you have more than one delay and if you have a system of differential equations. But to keep everything neat and tidy, we're just going to focus on this. So we're going to consider a Banach space X, which essentially represents what happens at present time and the history. And we have the classical continuity relation here. And if you do this, you can turn our first delay differential equation into some sort of ODE on the Banach space. Essentially, we are getting here, the point of it is we're getting a vector field. And this is going to be very convenient. So now that we have our vector field, we can look at equilibrium. So if we have an equilibrium of this vector field, then the eigenproblem, so if we take the Fréchet derivative of f and we evaluate this at the equilibrium, we're going to get this term here. So there's nothing very complicated here. We just take the Fréchet derivative of this right here. And if you look at the second row, you're going to see that psi of s, so the history of the eigenvector has to be equal to some exponential lambda s times a scaling parameter, which is psi. And then if you plug this in the first row, you obtain a characteristic equation. And an eigenvalue is going to be a 0 of this characteristic equation. So if you were dealing with multiple delays, you will have more here, right? You will have a term for each constant delay that you had. And if you were dealing with a system of differential equation, you will have a matrix, basically. Okay, so the parameterization method, once again, we're going to suppose that this our operator df evaluated at the fixed point has n distinct unstable eigenvalues and that they are non-resonant. So basically, there is no n tuple greater than 2 such that the characteristic equation has a 0. This is an important condition, and actually it has been mentioned before, and you have seen already why it is important for the purpose of invertibility. So we're going to look for a map that takes a subspace of, say F is, we decide to work with real sort of Rn, and then we're going to map it to our Banach space. So we map the origin to the equilibrium, and we ask that the tangent space at this point is essentially the unstable space, right? And now if you denote the flow of the original nonlinear problem that we care about, we're going to require that the unstable trajectories are sent to the trajectories in the original problem. Now, because we assume these two first conditions here, it turns out that this trajectory will lie precisely on the unstable manifold. Yes, capital lambda is just the matrix form of lambda. So if you derive this and evaluate at 0, you see that P must satisfy, in fact, a partial differential equation, which is equation 2 here. This is not so convenient to solve as of yet. So we're going to work a little bit more to find something that is computational. So remember that P is an element of that Banner space X. So it has two components. One is what happens at present time, and the second is the history. So equation 2 really means what I wrote here. And the second, if you look again at the second row, you can see that P sub sigma is precisely equal to P evaluated at exponential of lambda s. So really we have a rescaling, simply a rescaling. And so if we plug this into the first row, we are getting this partial differential equation, which is much simpler to deal with. Because if you recall what was said earlier, if you didn't have a delay, this is exactly what you're trying to solve if you had an ODE. If you have an analytic F, we know that the P is going to be analytic as well. And so we can focus at the Taylor coefficients for P. So the Taylor coefficient of P are elements of L1. And if we turn equation 3 into in the space of L1, we are getting this formula right here. So L sub lambda is just representing this operator here, and S sub lambda is just representing this rescaling that we're doing. So what's important here is that we can easily prove that, so F again is a polynomial, right? Which we evaluate, and we evaluate sequences on it. So we have a convolution, between the Taylor series. So, in this algebra, if you look at the alpha component of F, you can write it as the derivative of F times the component alpha of A plus some remainder term. And the punchline is that this remainder term is only the nonlinear part of F, and it does not depend on A, the component alpha of A. And this allows us to find an explicit formula for this component. So all of our Taylor coefficient for all orders greater than 2 will essentially be given by this formula. And again, this is why we wanted this non-resonant condition, because we are trying to invert the characteristic equation here, right? So we don't want it to vanish. So just to apply a little bit, to see what we need, what are the ingredients that we need. So if you have the Ikeda equation, so you only have things that happen at minus tau. You don't have anything at present time. So if you differentiate this, you get 1, the 3 goes down, you get 3, then you evaluate at your fixed point. And because you have u sub t, essentially this will pull out this exponential term right there. So very standard once again. As we mentioned earlier, the first terms of your Taylor series, the first coefficient of the Taylor series are going to be the fixed point. and are going to be the eigenvectors. And then how do we get the f hat? Well, we just look at the nonlinear terms here, which is just this one. And we require that a sub alpha is equal to 0. So it does not depend on the component alpha of A. Yeah. So we can do the same, just for the sake of the argument, we can do the same for a system of delay differential equations. Essentially, if you proceed in the same idea of what I explained, you're going to get a characteristic equation that is now, matrix. And, if for you just have to rearrange your terms properly here. And then at the end, the f hat is exactly the same idea as before. So here, for instance, first component, there is no nonlinear term. So this is just 0. This is, we don't care about this one. We don't care about this one. We only care about this term right here, which is what I wrote here, right? Okay, so it's very convenient, very easy to use. And we used it to actually compute a two-dimensional unstable manifold. Now, there is what you're looking at right now. So in orange, this is actually the trajectories that the particle follow on the manifold. And all of this is proven rigorously. And so now I'm going to talk about how we are going to prove this. So you have two options. Because you're dealing with an explicit formula for the Taylor coefficients, you can use a tail operator. So you use interval arithmetic to compute the Taylor coefficients so that you have a precise enclosure of them. So this, it's very important that the equilibrium, the eigenvalues, and the eigenvectors, you have previously enclosed them rigorously, right? So that's something you do beforehand. And then you use interval arithmetic, the recursive formula we talked about. And then you define essentially just the tail operator, which is going to give you control for the error of the truncation of the Taylor series. So it's simply defined. And again, we are blessed with an explicit formula, so we just use it. And all we have to do is to show that this tail operator is a contraction in a neighborhood of 0. Okay, so there's a big pro here, is that because you're looking at simply the truncation of the Taylor series, you're going to reach an amazing, your error is going to be amazing. And easily you can reach 10 to the minus 60 or something like this. And you have a better understanding of what's happening, what is the truncation error, and what is the error associated with the coefficient. There is a big cons, however, is that this is extremely slow because step 1 right here is very painful, very, very painful. So what you could do instead is to use floating point arithmetic. So I'm going to speed up here a little bit and define this operator G, which represents the zero finding problem. But the punchline is that you don't care anymore to do the recursive formula. You just do it approximatively, you throw it in G, and then you just show that you have a contraction with the Newton-like operator in a neighborhood of that approximation you found. So you don't really care to have precise Taylor coefficients. Yeah, okay. I guess I went a bit over time, so I guess that would be all.
I think you have one more minute.
One more minute? Okay.
You're doing great.
So to show that you have a contraction, I'm just going to show you one way of doing this. There's other ways, but it's the radial polynomial approach. And so the T operator that we talked about before, essentially you want to, okay, so you want to evaluate these bounds. None of them are very complicated, very straightforward. But what's going to hurt you the most if you use this method is the Z1 bound, because you need it to be strictly less than 1. And the two method I gave you, whether or not you want to use a tail operator or a Newton-like operator, they will suffer the same problem with this Z1 bound. So unfortunately, there's none of them that will help you really fundamentally here. It's more about the speed than anything else. Yeah, okay. So that I guess concludes what I wanted to say for today.
Thanks, Olivier. Okay, plenty of time for questions and discussion if people have questions.
I may.
Yeah, is that Michael?
So in the variation in the approach via the invariant manifolds, so to parameterize the invariant manifolds, there are the eigenvectors occurring, these psi vectors.
Yeah.
Right. And the rest of the computations depend on them. So in case of multiple eigenvalues, you have many choices for these psi's, and even in case of single eigenvalues, you can still scale them in length.
Absolutely.
And how much of the in how far do the results depend on this choice of the eigenvectors?
So
you just said enclose them, but not which choice you
well,
mean.
So in fact you choose, right? So here, for instance, so this is where I said you have to enclose them.
Yes.
So okay, so if you have a scalar delay differential equation, you pick any number you want, right? So that's okay. You can pick 1, 2, 3, whatever you want.
And that scales out. The choice you make scales out in the rest.
Yeah, exactly. And so at some point, you know, and if you don't want to scale them, you can just change your space to work in a weighted L1 space, right? So exactly, it scales your Taylor coefficients. And if you have when I say that you need to rigorously enclose them, it was more for if you're dealing with a system of delay differential equation, when sometimes you might not be able to put your hands on an explicit formula for them. And then you have to solve an eigen problem beforehand rigorously. And there are a lot of methods, actually with the Radii polynomial to do this. Yeah. So
it's clear you can enclose them, but how do you scale them for the further process? And which choice do you make in case of multiple eigenvectors or multiple?
It really depends. I mean, I usually pick one, if that's the question, if I understand you properly.
No, you can. When you have psi1, then you can also take 10 psi1. That's also an eigenvector. So
absolutely. So I fix them. Usually when I do this computation, I fix them. You know, I pick one and I see where I go. If it looks to be not too far, I can increase it, you know, and just rescale, as you say, and then 5, 10, and then until it breaks, and I know that, you know, I'm beyond the convergence of my series.
Can I make a comment? Maybe this will help with.
Yeah.
So Michael, these are analytic functions, right? So they're analytic on some domain. So you either, if you want to fix the domain, say to be the unit disk, then you choose the eigenvectors so that works. So you choose your scaling so that the proof works for the unit disk, your domain. If you want to pick the scaling of your eigenvectors, then you have to decide on what domain your power series converges. And these are kind of equivalent.
They're the same,
yeah.
Oh, okay. I see.
Yeah, and let me add that, you know, that at least in many of the projects I've been working on, one of the more numerically stable case is that, you know, you pick the length of your eigenvectors so that the decay rate reaches somehow machine precision with the given, say, number of modes that you're willing to work with, and then you do your proofs in L1, and that way the the L1 norms and the operator norms and all of these bounds, let's say, from the required for the contractions are much more stable numerically. So there's a couple of reasons to choose them so that they decay, and then after that you do the proofs in L1 for numerical stability reasons.
But theoretically, yes.
No, please.
And in fact, if I may complete this, when we use the Newton-like operator, so I went fast on it because I thought I was running out of time. And but essentially here, this is the scaling part that you're mentioning. This is a phase condition that imposes a certain number.
Yes.
So you fix that scaling, and then you do the rest, and you try to prove. And if it works, your scaling is good.
If it works, it's fine. And if not, you try to improve the scaling.
That's it. Yeah.
So that means that what my question was that so there is no a priori strategy to choose the scaling.
Not unless you knew where the pole was.
Yeah.
Right.
Once again, please.
If you knew where the poles of this analytic function were, you would know what to do, but you don't. So you have to play around and try to guess.
Yeah.
All right. Okay. Thank you. That's fine.
Great. Other questions?
Jay, I do have a question concerning the eigenvalues. I mean, so it is assumed in the first place that we don't have any resonance, right? I think that's the deal. But Olivier, I mean, what about in the case you have a double eigenvalues? You probably do have also an important part showing up in the linearization part. Then after that, you can be a bit of the prisoner of what Michael was saying about rescaling, because then if you rescale, you change also the important part. You see what I mean?
So we assumed that we had distinct eigenvalues. And precisely.
I take it back. I take it back. Well, I mean, I was confused because Michael says that.
So we do make sure that this is a nice problem.
Okay, so the eigenspace associated to that is always dimension 1. Okay, I see.
Yeah.
Okay, well then a part of what Michael was saying was not applicable.
No, we can have multiple eigenvalues. They
just have to be distinct.
Sorry?
We can have many dimensions, lots of unstable eigenvalues, but they should be non-resonant.
And
they should be distinct, for example.
Yeah.
All right.
But so it's just like in finite dimensions. If you have a resonance, you need to change your parameterization method to conjugate not to the linear system, but to some polynomial.
Yeah, but that's another story. That is not covered in this setting, right?
Exactly. Well,
okay, sorry, Olivier, sorry.
Yeah. No, that's all right. I mean, it's good that you mentioned it because it is an important thing. It is very, everything relies on these assumptions.
All right, okay.
Great. Any other questions?
Perhaps I can add something just quickly. If anyone is interested in using this technique, so in the paper that we wrote, we use the Taylor, this tail operator. It's good because it flows nicely. You know, it's very straightforward. You compute everything rigorously, and then you just handle the truncation. But if you don't really care about the truncation error necessarily, just you want some sort of C0 bound, I would definitely recommend to use the Newton-like approach instead. This is going to save you so much time. I mean, we couldn't prove some manifolds because there were just too many modes to compute, and you take at least 2 days to just do the the rigorous computation with interval arithmetics. So.
Well, in some sense, even if you take 2 days, if you have a proof finally, that's fine. So, right, if an analyst sits down and writes a proof, it might take several weeks.
Yes, but if you can do it in 10 minutes instead, that's
then it's better.
Even better.
Okay, well, maybe it would be a good time to thank all of the speakers one more time. Really